Hi everyone, and welcome to another video from Programming for Data Analytics Part 2. Today we're going to be looking at logistic regression, scikit-learn libraries usage of that. And so in the past we were looking at linear regression, which is a continuous variable prediction. And now we are going to be looking at what is known as a classification algorithm, in which it's not a continuous variable, but you're actually just picking between, well, in the case of something like binary classification, you're picking between two classes, but really you pick within a predefined number of classes. And that's really what you're trying to do with a classification algorithm in comparison with a continuous variable algorithm like linear regression. And there are multiple algorithms that can do classification, support vector machines, neural networks, obviously logistic regression. So we'll explore a lot of them, but we started with kind of like the somewhat simpler one, and logistic regression is really kind of like the OG and the most basic one that you can really do in general, and also in scikit-learn. And you'll see that when we actually get to the code, it's going to be pretty simple code. It's not, there's a very small deviation from the linear regression one. Really, the hard work is preparing, like usual, your data sets. So that's where most of the work is. In the case of logistic regression and any classification algorithm, your expectation of the output is no longer, like I said, a continuous variable. It's a group of classes. And so you have to decide what those classes are, and you have to represent them numerically. Like if you have three classes, multi-classification, then you could say they're like 0, 1, and 2, right? And you tell that to the algorithm so that it knows to do this classification that way. But also, it could be as simple as a yes or no. And in the next video, I'm going to go through an example that is like the basic with the built-in data set from scikit-learn, and I took an example from scikit-learn documentation, and I'll show you that. But in the next video, I'll go back and revisit something like the crypto data set that I was working on my example, and maybe we'll do a classification problem on that. Probably we could do something, instead of trying to compute the Ethereum price, which is like continuous variable, we can do something like whether the Ethereum is going to go up in price or down in price that day. And that's a classification that belongs to a group of up or down. So it's very easy to separate. So that's just an example of what we can do. But anyways, I wanted to refresh on the math to make sure that you understand what is happening behind the scenes. So with something like binary classification, the idea is that you still feed it the same input as before. And by that I'm saying it's just a bunch of features that you expect have some sort of, ability to predict the output. So you want it to be something relevant, right? So if you're trying to predict, again, whether something goes up and down in price, then it has to be information related to, what's going to happen. So like if you're trying to decide whether something is a cube or a triangle, well, you gotta feed it something relevant to that. You can't just feed like the weather if it has nothing to do with it, okay? So you still need to have features that are useful. And you're still gonna have a training set and a testing set. Your training set's idea is that it's going to teach the model, what the pattern is basically, or what the features allow it to deduct that can actually lead to the correct prediction. And that training set does need to contain classes, and the classes are going to be the different predictions, and they have to be a finite amount that you set. Obviously, the most basic example is a binary classification, which you have only two classes, which it could be something like class A or class B, 0 or 1, -1 and 1. And so you say, okay, I'm going to predict one of these two classes, and that's all the algorithm is going to do. So in your training set, you're going to feed it a bunch of features, and then you're going to feed it what class that example belongs to. And then the algorithm is going to learn that, so that then when you feed it a new set of values, so like, if you have multiple weights, you feed those in, then you hopefully get the right class. And so that is still going to look like something like this when it comes to your formula. So while you're not computing a line per se, Well, actually, in a way, you kind of are, right? Because if you think about like a 2D graph of points, and you're trying to say, okay, this is what I currently have, the two classes, you know, my dots and crosses here, and you're saying, okay, I want to separate these classes. I want to separate these into groups, and then if I come up with a new dot, then I know where it belongs. Then technically, you're drawing a line, right? You're still drawing a line, and so you're saying that anything beneath that line belongs to one class, and then anything above that line belongs to another class, right? So you can still picture it that way. However, that only kind of works if you're thinking of two classes, because then if you do multi-classes, and it's not really a line, it's like a multiple lines or curves and things like that. But in the most basic sense, you could still visualize it like that. And so that line's going to have a slope and whatnot. And so we have our weights, which are going to be something like whether it's one weight or multiple. So if you only had two features, then it would be something like this, W1x plus W2x plus your bias, which I'm just going to say is W0. And you're still going to try to get a prediction out of that, or the generalized version that I wrote here all the way to Wn. And so now we kind of have to revisit what it means to correctly predict something, right? So the issue that we have with continuous variable is that it doesn't make sense to just say whether something is right or wrong because it's a variable. Like I said, you know, if we create a model that is really good, it's just off like in predicting amounts of money, like the Ethereum price, but it's only up by a couple of cents. That's still a pretty good model, even if it never gets it right to the penny, you know? But when it comes to classification, it's a lot easier because if with classification, with binary classification, you're only expecting two outputs and the model can only come up with, you know, one or the other, 50-50 chance in a way. I could simplify, but yeah. Then you can just say whether it's right or wrong, like very simply. You have an accuracy. So we can actually look at accuracy as something measurable that is good, because there's no like, well, you know, we're getting like mostly class A but a little class B. No, we're saying you either pick one or the other one. And so we can actually use accuracy as a way of measuring it, but we can also do additional measurements, such as like when we get class A but we want it class B is different than when we get class B but we want it class A. And so we're going to revisit kind of some metrics for that in the next video, like precision and recall and true positive versus false positive and things like that. So for now, we'll keep it simple with accuracy, but I wanted to talk about that because when we're trying to figure out whether the model works or not, we want to look at what's known as the cost function, also known as the loss function. So it's either called cost or loss function, one or the other. And so what that function is, it calculates the error in our model. And we want to get the least amount of error, so we want to minimize it. So if you try to graph that minimization, you can think of it like a parabola. And what we want is the least amount of cost that we get on those parameters. So the parameters, you know, they could be really big numbers or something. And the bigger the number, eventually, if we have a perfect spot, which is the bottom of this, so we want to get the bottom of this because that's the one that gives us the least amount of cost. The higher the cost is like the bigger the error, okay? So we want the least amount of error. So we want that to be the lowest point here. So it's going to be like basically the lowest point in the parabola. And if our parameters are off by that, like they're higher than they should be, then the cost is going to go up. But technically also, if they're lower than they should be, then the cost is also going to go up because it's like, you know, too little, too big, or just right. And we want it just right. Too little is not good and too big is not good because it's not going to give us the best accuracy possible per se. It's going to be a bigger amount of error. And so we want to minimize that. And that's how we get this parabola. And that minimum point, we call that like the optimal point or optima. And if it's the best point of the entire graph, which in the parabola there's only one of them, we want to call it the global optima. Now there's going to be more examples in this little parabola, so the word global is going to come into play more in a second. But just kind of looking at this again, what we're if we're trying to figure out where we are in this line, you will see that you can look at the tangent of this line, right? And wherever the tangent is a 0, so like it's flat, the slope of this tangent is equal to 0. That's really where we want to be, because that's the lowest point, right? Nowhere else in this line is the slope 0. Like, for example, if I go and look at like this over here, so this point here, so the point right there, if I look at the slope of that point, I look at the tangent line. That slope is going to be like a 1, so it's not a 0. And then over here, it's going to be all like a negative 1.5, right? That's what that tangent is. So the lowest point is the slope 0. And how can we figure that out? We just take a derivative, right? And so wherever the derivative of this slope, or of this quadratic equation, of this parabola, wherever the slope of this parabola is 0, that's where we want to be. And we can get there by just getting the derivatives and then keep adjusting it a little bit up or a little bit down until we get there, right? If we have a negative slope, then we got to keep going. If we got a positive slope, then we got to go the other way. And that works as long as it's a parabola. Unfortunately, though, it's not always a parabola. And sometimes it could look more like this. There's things known as local optimus. So it might be something like this. That's a little bit more fancy than it should be, but yeah, we'll call that the function. So we have it's our cost function's result. So we got cost and parameters still. Now in this case, what I'm saying is that the lowest point, the ideal point, is probably right here, right? This is actually where we would want to be, the global optima, because that's the set of parameters that is going to give you like the best result. Now notice something, and I didn't mention that, but even in this example up here, even the best point still has a certain cost to it. This is not a 0. This is like maybe like, let's say it's 0.5, okay, or whatever. That's because I'm saying that even in the best case scenario, you might still have a degree of error. It's possible. It's possible that there's no way to actually have a perfect solution for this. So just want to point that out. There are models that can have perfect solutions if the features are rich enough to get that, then that can happen. But it's not always the case. So you can't just rely on that on that being a way of finding out. So that's why it's not at 0. So I just wanted to point that out. But anyway, it's the same here. It's not at 0. And so we want to call this the global optima, right? Because it's the minimum point. However, I want to bring your attention to also these ones here. This here, that here, and then maybe this one here. These are known as local optimas. And so what they are within their own little areas. So for example, this first one, within like the area here to here. In fact, maybe let me actually highlight it. That'll be easier to see. So within this area, this is actually the best spot. The one's going to give you the best values. And if you're just doing what I said before with the derivatives, where you're just kind of, if it's negative, then you keep going. And if it's positive, then you go the other way. So like if you're here, you got to keep going. And then it starts getting higher. So you're like, oh, nope, I guess if it's getting higher, let me go back here. And so you end up at where the best spot is. So you can think of it like a ball. You drop a ball, it's going to roll past the minimum, kind of go up a little bit. But then gravity's going to come back, and eventually it's going to settle on the lowest point, right? Well, okay, sure, but if the ball's going fast enough, it might actually jump over this and then whoop, kind of get stuck there, right? Technically, if you throw the ball quick enough, it might go like whoop, and then get stuck here, right? And so you run into these issues with this, sort of throws that you call like little holes, little valleys, hills and valleys, and you have that issue. So it's not enough to just kind of guess, oh, the slope is negative, let me keep going. Oh, the slope is positive, so I must have passed it. It's not enough to do that because you might be stuck in some local regions. So what's the way around this? Well, there's a lot of different ways to approach this, but in the basic sense, when you're checking each step here, you can go into tiny little steps each time. And then once you see higher, you go back in tiny little steps. You can go in big steps, like all the way here, and then hope that you bounce in the right spot, but that might not still work. Or you can do different ways of guessing that minimum. And so basically trying to find that optimization is a hard problem. And there's a lot of different ways. There's like linear, quadratic approach, etc. But ultimately, it kind of boils down to what I know as the solvers. And the reason I'm bringing this up is because this is a very important parameter that you want to look at when you're looking at your logistic regression model. And so within these, we have a couple, I believe five that we want to talk about in scikit-learn, and they are going to be Newton's method, and then we have this one I gotta copy the name now because it's pretty tricky. Yeah, so this is a limited memory. In fact, here, let me just use the abbreviation actually first. Otherwise you will never remember. It's LBFGS, which stands for the limited memory Broyden Fletcher Goldfarb Shano solver. And then this Newton one's called the Newton OG. Or sorry, not OG, CG. And these are the abbreviations that you'll see in scikit-learn, so that's why I'm writing them down. And there's this one. And the idea is these are different ways of finding that minimum. Ideally the global one, but if not, then at least within the local ones, one of the better ones, right? The most basic sense, like I said, is just to bounce around. By if it's negative, then you make it positive, and if it's positive, you make it negative. But that's when they get you stuck in the first local minimum that it sees. These ones go more hardcore than that. They got more fancy approaches. So we got Newton's method, we got the LBFGS method, then we got what's known as the linear one. This one stands for Library for Large Linear Classification. We got SAG, which if you remember from a couple of videos back, that's your stochastic gradient descent. The difference between that one and the gradient descent that you saw in the other video is that I believe it uses a random sample based on previous gradient descent, and then it's just an incremental grade aggregate. So it's just a slight variation, but that's going to be the closest one to the one that I went over when I did a couple of videos back to the math of machine learning. And then you have SAGA, which is an extension of the stochastic average gradient descent. Yeah, that's all I'll say, because I'm not going to go deep into talking with like L1 and L2 regularizations and things like that. But yeah, it's basically faster than this one, so it's like better than this one. In fact, let's talk about that. So when is one better than the other one? And so it's a little harder to explain than one would think, but you know how I was talking about the first derivative for trying to get the slope? When you're trying to do the calculations for this, it's not, sometimes you want to actually go beyond just using a line for like tangent, and you try to actually do quadratic and to like match a quadratic function within the parabola. So that gets pretty fancy. And so the Newton method is basically computing the second derivative because of that. And it uses what's known as a Hessian matrix. So maybe I'll write that term down. What you should know is that it is slow for large data sets, okay? So if your data set is big, then here I have some pros and cons actually. Let me find it. Yeah, so if your data set is big, because of this second derivative computation, it's computationally expensive, so it'll kind of slow down. And when it comes to like multivariable optimization, it has it attracts what's known as a saddle point, so a little bit of a downside to that. But it's pretty good though. Just think of it like a twisted gradient descent per se. Okay. The second one, the limited memory Boyden Fletcher Goldfarb Shannon algorithm, is basically going to it's going to be better, I believe, than Newton when it comes to large data sets. Oh, by the way, important to know, it is a default one in scikit-learn. So this is the one that actually if you just don't put any arguments, it'll run this one. But it saves memory. So it's not that amazingly fast with large data set, but it's a little bit better than the Newton method. But the real advantage to it is it saves memory. So if speed is your concern, it's not going to help you too much if you have a lot of memory. Okay, but it's a good fit all kind of scenario, with the exception of it being still kind of slow. The third one is the library for large linear classification. The big downside for this is that it cannot run parallel, and it's not good for multi-classification problems. So it's mostly just good for like binary stuff. And in terms of like, I mean, well, actually, it can do multiple variable classification, but the way it does it is it compares one variable against the rest. So like, does this belong to this variable or the other variables? And then it moves to the next variable. Does it belong to this variable or the other variables? Instead of like saying, does it belong to A, B, C? It says, does it belong to A? So like, does it belong to A or B, C, and D? And then it has to check, does it belong to B or A, C, D? And so on. Does it belong to C or A, B, D? So it does it like that, versus like truly checking whether something belongs to all classes at once, which the other ones can do. And it can't run in parallel, which means you can't like multi-process this and like just make it run faster that way. But because it can do this like weird thing where it says one or the other classes, it works really well in high dimensionality within this limitation. So yeah, it's a good thing and a bad thing per se. It used to be, I think, the default in scikit-learn and older versions. So you got to double check what version you're running, because it used to be. I have that as a note here. What else do I want to say about it? The algorithm that it uses, if you're curious, is known as a coordinated descent algorithm. And it solves the problem by performing approximate minimizations along coordinate directions or coordinate hyperplanes. Okay. Stochastic average gradient is basically like very similar to just gradient descent in general. It will converge faster than normal gradient descent, and it is definitely the faster approach for large data sets. So yeah, I think I'll say that enough about that. Just basically, if you want speed over large data sets, then this is going to be your advantage. But it is very expensive when it comes to memory, which might make it impractical. So that is going to be your issue with that. And yeah, basically the difference between that one and the Saga is going to be optimized for like very, very large data sets. So basically Saga is good for large data sets, but like really, really large ones, because of that memory issue and whatnot, you use Saga. Okay, so I think that's all I'll say about the different solver methods. The difference between some of them, though, like, whereas one method might take like an hour to finish, the other one might take 1 minute to finish. So if you're really interested in optimizing it, you should look more closely into what these solver methods do and how they work, and compare to what you're trying to do in terms of the number of classes you're trying to do, in terms of the size of the data set. Those are going to be your big decision factors. Is it binary classification or is it multivariable classification? Like, 5 classes you're trying to do also. Is it a large data set or a small data set? Do you have a lot of RAM, or do you like a lot of memory, or do you not have a lot of memory? And once you make those decisions, then you can go ahead and decide which solver you want to use. And then, like I said, the difference will be huge in time. So something to be aware of. I wish I could go more into it, but it just gets too technical, so not really worth it. But yeah, okay. So I think that's enough of that. Let's just jump right in. And like I said, today we're just going to do sort of a pre-made example that is from documentation, and then next time we'll do our own thing. So this is the logistic regression. I'll leave a link on the description below for what we're going to do. And also here, actually, let me show you the solver function, or parameter, I mean. Here we go, solver. And so this by default is going to be the, like I said, the LBFGS one. And this, I mean, I guess the too long didn't read version of the solver is right here for you. It says for small data sets, liblinear is a good choice, whereas SAG and Saga are faster for large ones. For multi-class problems, so that's when you have more than 2 classes, only Newton, CG, Saga, and LGBFS handle multinomial laws. Liblinear is limited to 1 versus rest schemes. That's what I was talking about with like A or BCD, and then like B or CDA, and so on. And that sort of thing. What's this warning say? The choice of the algorithm depends on the penalty chosen. Okay, yeah. So this is the big one. I mean, random state, of course, you know what that is now. You know that, like, that's so you have predictable results, because these things do start, and like especially when it comes to minimization of finding that the optima, you got to start somewhere in that parabola, and depending on where you start, you might find a different optima, like you might end up in a different local optima that might not be the global one. So randomness can really screw up accuracy, whereas you might see something really good, but then the next person might not. So that's why this random state exists again. So you know that one. Right now you also know solver. So I would say that's the most important one. There are other parameters that you should optimize. Penalty being a kind of important one that you should look in your own into. But at least those are the ones that you want to play with. Solver, set the random state to something, and maybe read into penalty a little bit. Okay? So yeah. With that said, this is the example we're going to be doing. I'll also leave the link in the description below. But for us to do it, first we need to explain what the iris dataset is. So the iris dataset, and this is also found in the same book I used for like the other one. So there's this book. It's very popular. It's a built-in dataset into say scikit-learn, again, something so that people can kind of try out these algorithms with something that is well known and there's tons of help online with. And let me go ahead and read from the book the description here. So the iris flower dataset is a particular dataset used for the first time by Sir Ronald Fisher in 1936. So pretty old. Well, old within reason. It is often called the Anderson iris dataset after the person who collected the data directly, measuring various sizes of the iris flower. In this data set, data from 3 different species of irises are collected, and those are the iris silky, virginica iris, and iris versicolor. And these data are corresponding the length and width of the sepals and the length and width of the petals. Let me draw a flower for you, or attempt to at least. Maybe I should have I'll draw it. So say maybe I can find a picture online. Okay, so these are the petals actually of the flower, and these are the sepals. And so you can think of like the height and the width of it, and same here. To decide amongst the 3 classes, which are the 3 sort of species of flowers, we're gonna see if we can figure that out based on the shape of the flower. So based on that height and width of the petal and the sepal. So, I don't know, but like let's just say maybe like the ones that have really long petals are maybe one class, and then the ones that have like really short petals are the other class, and then for the 3rd class maybe it has to do with the sepal. That's just like a wild guess, okay? Let me see if I can find this picture, like a picture online. Actually, maybe we can see the flowers themselves. Yeah, this picture is cool. Link broken. Hold on. I really like this picture now. There we go. So I'll leave the link to the picture in the description below. But here we have the 3 flowers. And you can see the petal and the sepal. And they're a lot more similar than I thought, to be honest with you. Actually, no. Because the petal itself is here. See that? These little thingies. And the sepal is the thick ones. So you can see the 3 flowers look somewhat similar. I mean, at least to me, well, this one looks a little more different. But these ones you can see, like, you can definitely see how this one, I mean, obviously this is one sample of a flower, but you can see how the petals definitely look longer on this one and definitely look shorter on this one. And this one's probably like medium, so I wouldn't be able to figure that out based on the petal length. But you can definitely see the sepals very thick here. And this one's like, again, like middle ground, but it seems like these ones have shorter sepals but thicker, whereas this one's more rounded and this one's just longer. So maybe that's what the machine learning can pick up on and say that this is like really thick sepal, short and thick sepal. This one's like about the same length, about the same height and width, and this one's like all about the height for sepal and like very little width for the sepal. But definitely the middle one's the one that's tricky, It's like, it's different. Like this one's got the short and stubby petals, and this one's got the long one petals, but between this and this, the petal length is kind of gray zone. But then you can look at the sepal, and then the thicker one's going to decide it. So that's what I would go with. Yeah, those would be my rule sets. I would say really short petal in relation to the thick, the width of it. I would go with the Iris setosa. If I have really long petals, then I would go between the Iris versicolor and Iris virginica, and to decide between those, I would look at the sepal. And then if the sepal is wider than it is long, I would go with the versicolor. If it's longer than it's wide, I would go with virginica. So that's what I, in my own personal machine learning model head, would decide. Obviously, this is one sample, but if I was looking at a lot of samples like the machine learning model would look at, maybe it would pick up on cues that I don't see, right? And so that's what the data set is. It contains those 4 dimensions. It contains the length or the height and the width, so whatever you want to call this and this, of both sepal and the petal, okay? So now we go back to my picture. Maybe it makes more sense now, okay? Maybe if I put the little like hair looking things on those, it looks more real now. And maybe purple it. And like a lighter tone of purple. Do I have a lighter tone? Well, I have this. Oh yeah, there you go. Clearly this is not an art class, but I think that didn't need to say that either. Okay, so looking at the data set, what does the data set contain? The data set contains 3 classes, the 3 flowers that I said. Each class has 50 samples, so that's really nice because we don't have to worry about that class balancing that I mentioned at some point. I believe I mentioned it on like the first scikit-learn video. That you ideally want to, when you're training, you ideally want to have the same amount of samples per class, particularly when you're doing classification algorithms. Because if you don't, then you bias your algorithm. Like if you have a model where like you have 99 of one class and 1 of the other class, your model is just going to be like, yeah, it's just going to be the class with 99. Because like already there, by just making that assumption, it's going to be 99% correct. So like, yeah, it's going to be like, yeah, I don't even do math. I'll just be like, I'm picking this class always. Screw the 1% that gets lost, right? It's going to do that. And you don't want that. Because like, your training data might be biased, but in the real world, maybe it's not biased. Maybe you just happen to be unlucky finding flowers of the other types. So you have to balance that out using imbalanced learning techniques like SMODE, Edison, etc., etc. Extrapolation at least. But yeah, so here you don't have to worry about that. You got 50 of each, and so a total of 150 because you have the 3 classes. You have 4 dimensions per se, those 4 features that you're looking at. And yeah, I mean, it's a pretty nice and simple data set. So let's go ahead and try it out. So the first thing we're going to do is I'm going to go ahead and import the scikit-learn library for logistic regression. Okay, so I'm going to say from scikit-learn linear models, I'm going to import, and before I imported linear regression, this time I'm going to import logistic regression. Okay, also I'm going to import the dataset because like I said, you don't need to download the dataset. It's already built into the library of scikit-learn. So I'm going to import datasets so I can do that. Because I am going to want to draw stuff, before I forget, I'm going to import matplotlib, pyplot, just like I was doing in the other videos. And just in case, because I think I'm going to need it, I'm going to import numpy as well. Okay. Why is that underlined? Import matplotlib. I don't know. But let's just run it and see what happens. Valid error. Oh, this is not from, it's just import. Okay. So first thing I want to do is I want to import the data set, or just load it in basically. So to load in, and like I said, this is coming from this example, so I did not come up with this example. This is part of the documentation of scikit-learn. But I still want to show you line by line, and I am going to slightly tweak it. I want to load in the data set, so I'm going to store it in this variable called iris, and I'm just going to call dataset, plural, load iris. Okay, so that loads the data set. So let's say you didn't know how many features or how many dimensions it had in general, then you can just go ahead and say, well, actually, here, let's just try to say print iris and see what we get. There's some documentation, I suppose, at the end of that. You can see there's a lot of information there. Okay, amongst that, there's documentation probably about where it came from. But if we say data from that, and I think we're just going to get the data itself. Okay, here we go. So this data shows you each of the samples, right? There's 150 of them. And you can see here we have probably the four measurements, right? And I don't know if these are in centimeters or millimeters, but it doesn't really matter. But it's the length and the height of the petals and the length and the height of the sepals, right? So there's some numbers. You see that we don't know, like, okay, but which flower is this? Flower 1, 2, or 3? That's stored under the target variable. So if I do this, that's a little array. At the bottom, that says which class they belong to. Now, in this case, it's nicely ordered. So like the first 50 are actually from the first class. I don't know which one that is. Probably the somewhere in here it tells you, but it's one of the flowers. And then the second 50 is the other flower, and then the last 50 is the third flower. So that means that this and this are all from the same flower. You can see the numbers vary though, but at least I'm seeing that this number is always bigger than this one. And then like, same with this number being bigger than this number. So there's that. So yeah, we can see the data. Now, let's say I don't know how many there are. You can just call length on this and see. So, you know, comment this out. You can see there's 150 rows, so 150 samples. And then wanted to see how many features there are per row. You'll see there are 4. Okay, so there's that. If I wanted to print a specific one, I could say something like print iris data set or data, I don't know, 50, followed by the target of 50. And that tells me that class 1, we have these 4 measurements of that specific flower sample. Okay, so the data is just there. We don't really need to do any kind of cleanup because we have it. The only thing I'm going to do is, for now, because we saw the fun that it is to draw multi-dimensional graphs, I'm just going to stick to just taking 2 features and seeing how good I can get with just 2 features. Obviously, 4 will be probably better, but I'm going to go with just 2. So I'm going to go with the first 2. So I think that's the petal length. But it might, I'm not 100% sure. Oh, here, oh, by the way, if you do target names, that's on the book one. You can find out what the flowers are. So here, let's just do that really fast. Target name. Let's see if that works. I don't know if it'll work. Maybe not. Names, plural. There we go. So I guess 0 is Setosa, 1 is versicolor, and 2 is Virginica. And remember, versicolor is the one that looks kind of ambiguous. So that's kind of cool. So I'll leave that in there. I'm glad I looked at the book. Now, what was I looking at originally for? It was to find out, oh yeah, which are the first features, like what do they represent? What does this say? Yeah. So the first features represent the sepal length and sepal, I guess, length as well. So like X and Y axis. So like one is probably this way and one's this way. So very cool. So we are going to basically just take two features and that'll be our X. So I'm going to take all the first, this is your list comprehension. This is taking all 150 of the rows, but only the first two columns. So I'm going to say 2 here, okay? So just the first two columns. So if I went ahead and print X right now, you would see it just got the first two columns, just like that. And so that's what is going to be my input. Okay, now my prediction is the Y, it's just the target for that. So I'll put it like that. Okay, and so again, if you want to see that, well, it's going to be the same as target. So yeah, no need to show that because I showed it already. Now I'm going to go ahead and make my model. So I'm going to call the logistic regression function to make the model. This is when you can decide things like the solver. So I'm going to go ahead and put for random state 42 because I like that. And the solver, I'm going to go with the default, but I'm still going to explicitly mention the default just because I think that's a good idea. Because as you saw back in the day, scikit-learn was using a different solver as the default, and then it changes to a specific version. That could happen also in the future where they just decided to use a different one. And so to play it safe, it's better to be explicit and not hope that, it doesn't change. So I'm going to at least put those two in there. Okay. All right. Moving on. Now it's just now let's train the model. So how do I train the model? The same way I trained the linear one. I use the fit function. It's pass in my features, pass in my predicted my expected output. And then I'm good. Like as you see, this should start to become familiar by now. How the only difference is now I'm using this function instead of linear, but I'm still using my fit function. And guess what? How am I going to evaluate this, whether this is good or bad? By using the predict function. In fact, I did cut something here. I technically I didn't do my test and predict split. So maybe I'll go back and undo that in a little bit. Because right now I'm training it on the entire data set. So, what if I want to test it? So should I do that now? Yeah, we'll go back and do it. I want to, in the example, the default one, they don't. So that's why I didn't do it. But maybe I'll go back and do that. But yeah, you can just use the same function that you used before. So if you recall from here, from the crypto one, we have the, where's it at? Train test split right here. Then you can do, and then you can also set a specific random state for that. So the splitting happens the same way. Oh, I never actually gave it a random state for here, for this linear regression. That's okay. But yeah, so you can just use that. You just have to pass in all the parameters. In fact, I'll copy and paste this. And leave it commented out for now. Okay, but anyways, at this point, we fit it. Let's go ahead and see how good it is. So even though we've created our prediction, we can just test it with its own input training data and see just how good it is. Like, how good did we get? So like, now that we've tried to find our minima, we can see just with the own data set, like the original data set, like where are we at? Just with the full data set, we just want to test it. So let's just go ahead and print out. Okay, let's store in the variable score the accuracy of this thing. And to get the accuracy, there's a function called score, and then you just get that information directly from there and then feed it back its own input. And we can see an 82%, 0.82. Now, very quickly, let's try to change this to a different one and see what happens. So let's do Saga and run it. And here comes one of the issues with Saga, actually, that it may not converge at all in time. And by converge, I'm saying is it might not find the minima before each of the loops. So every time you, so let's go back to the drawing board. Every time that we're choosing a dot, so like we start here, we do all our computations to find out the cost of everything and then do a second guess per se that is like less or more based on where we're at. So like next time we go here, and then hopefully from there we go here, and then here, and then here, and then here, and then here, right? So that's ideal world scenario. Another ideal scenario is to just go like jump, 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 and then from there we see we're kind of in the same spot, so maybe it jumps back here, back, and so on, right? So the difference between each of the dots, that's, you can think of that like your well, actually has a name. Is it the alpha? Your learning rate. It's called your learning rate. The bigger the number, the bigger the jumps. But a bigger jump, which can get you faster to your goal, but it can also skip over your goal, right? It's like, imagine you're throwing the ball with more speed at the beginning versus slower. A smaller learning rate makes sure you don't miss that minima, but it takes longer to find it. And so converging on the minima is what you want. That's when the ball stops moving. So here, what the error we're getting is that the max iteration was reached, which means that the coefficient did not converge. This is telling me that like when it was trying to solve this, it eventually could not find an ideal spot before it just hard stopped because we set there's a default built-in maximum amount of times that it can do a guess. It's one of the parameters in here. Oh wait, that's not the one. Sorry. Parameters, dual to fit, scaling weights, max iteration. Max iteration default is 100 of these, and so if I change that, I can make it try to keep guessing for longer, but it's going to take a longer time. So after 100, if it hasn't converged, it just gives up. Now, it's not always a bad thing because like you might just be jumping amongst two perfect spots back and forth, and they're both really close, but like you're just jumping back and forth like this really slowly. So it might actually be a good thing that it just stops. So it's not always going to improve things, but let's try it out and see what happens other than slowing it down. Let's try 500. You can see it's running for a while, but you can see, look, the accuracy actually went down from the last time I run it, which was with 100 iterations, which actually gave us back the 82% that we had. So like same as the other one. So you can see that it's probably bouncing back and forth between those. So yeah, all right, let's try another one. Let's try Newton's CG method. Let's see what that gets us. 82. So you can see that all methods are kind of giving us the same thing. Don't assume that means that it's always going to give us the same thing. It's just because it's such a short, small data set. It's not really making much of a difference in terms of time. It's not that noticeable. Here you can see the lived linear gave us actually a 76%. But if we let that run for longer, actually it's probably the same because it's converging already before it hits 100. So yeah, I think SAC's the only one we haven't run yet. 81. So you can see they all kind of gave us about the same, except for lived linear, which was a little bit lower. But we're gonna leave it with the default one. What I do want to show you though is if I decrease the iterations like very, very low, like let's just say 3, then that's just way too fast and it's probably going to give me low accuracy. See that? 64%. It's also probably yelling at me. Oh, because it failed to converge within that. So yeah, because I stopped it early. In fact, if I go and say just one iteration, probably gonna give me like a really random number, 33%. But if I try if I change the random state here, it could give me something really good or really bad. It's like spinning a die at that point. You know, where are you gonna start? If you happen to start at the right spot, you just get lucky. It's like winning the lottery. So, but in general, you're gonna get something pretty bad. You can see as the iterations go up, though, it'll start to get closer. 73 already by iteration 5. 72. Let's try 50 now. 82. So by 50, it's all good, but it's still not converging. But if you go back to the default 100, then it does converge. Okay? So you can see even at 50, it's like pretty much there, but it's almost still working. There's probably a lot of numbers after this digit that we're not seeing. So, yeah, I was thinking of a second if that was the right thing to say. But yeah, okay, let's visualize this. So like, I want to see how this classification is happening, okay? Then we can go back and change the whole training and test. So to plot it, I am going to just skip some of this and just copy and paste from the example, because I don't want to deal with having to plot this. Basically, you have to. We're gonna have to color it, and so it's a bit of a mess trying to do this, because we're trying to color a section of the line, like we saw how we saw it when I color this up here. You know, we're trying to tell matplotlib to color either the top or bottom. So that's basically what's happening there. And then let me just get the rest of the plot in there. Again, I'm mostly focused on the logistic regression part. The last video, we already showed you how to graph things for a couple of videos. And in the next video, I think I'm going to, well, not maybe the next video, but at some point, we're going to look at principal component analysis. And we'll talk a little bit about how that helps us to graph. So we'll revisit graphing. But for now, I'd rather just skip doing that, because we get to see the actual graph. So here's what the graph looks like. This looks pretty. The colors represent what our algorithm is deciding as the areas where it would belong to a certain class. So if I pick the point up here, it would automatically belong to the blue class. Same here. If I pick something here, it would belong to this orange class, this light orange as well. You can see that there are mistakes. So for example, this one here is near the border. However, it is belonging to this class instead of this class, according to where the line is, even though it should belong to the bottom one. So like, shoot. There we go. Well, it's a little bit too zoomed in, I think. Maybe there. This is easier to see. So you can see that that one's in the borderline, and these ones here are borderline too. This one here is good, but then this one belongs to that. However, you could say, well, shouldn't the model like kind of curve like that, or kind of curve here? Yes and no. You remember, you don't want to do overfitting, and doing all those curves is like just begging for having troubles with overfitting. Particularly here, like you have this sort of group right here, right? So this should kind of like dig in here. But if you do that, then that's just terrible overfitting compared to these. And I think that would end up badly. Probably what a better model would be just to completely curve this way a little bit. And then here, I think that this is doing pretty good job here. But something like this, you just can't do anything. It's just, I guess, nature mutating or something. But yeah, this looks really pretty actually. So that's your classification. That's all there's to it. There are lines, as you can see, because at the end of the day, this is still linear. I'll show you support vector machines and neural networks later on, but you're still in a way doing simple lines. It's just more than one of them because you're doing multiple classes. Like I said, if you wanted to do training and testing splits, you can do that. You just pass in the X and the Y. Do the same splitting. And then here pass in the X train and the Y train. And that's actually how it ends up with that. So you can see with the Y train, the accuracy is still good. Did I feed it right? Let me just double check. Yeah. So interestingly enough, with the training of the Y, of the 80%, it actually got the same result back. The line's pretty much the same. We got about the same amount. All the blue's okay. That's the one that's easy to remember. So you can see that actually the model trains really well even with less than the 50. By just giving it the, 40, it's still pretty successful. Let's go down to like 50, like half and half. Here I should expect it to kind of start going down. Well, it only went down a little bit. It went down to 80%. The blue ones here is in the wrong class now. So the line's a little bit off now here. And here it seems like also it's a little bit more this way, but maybe not. So you can see that eventually you get to a threshold. Like if we go to 70 now, we're only getting 30% for training. It's going to start to get messed up. Wow, it's still pretty good. So these plots must be very obviously separable. We go to like 90. So that means we're only getting 10%, which is like literally like 5. Yeah, so here we get 62%. So this is one where like it's doing a poor job. The blue one's still succeeding okay-ish, but the orange just took over. Probably because we're only getting, if you think about it, we're only getting, of the 50, we're only getting 5 samples now. And there's 3 classes. So there's probably 2 or even 3 of this class. And so this is the bias happening here probably. Probably getting, or we're getting 2, 2, and 1. And so that's why this was like really just like punished. But of course, this is just showing you that you should have ideally a large data set. Because even then, if you did some weird split like this, you'd still be okay. But yeah, that's going to be the logistic regression. Just a brief example based on documentation. In the next video, we're going to explore this deeper and try out our own data set with the crypto. And then I'll show you more about evaluating it and maybe look a little bit about principal component analysis in that video, or maybe I'll leave it to a future video. Don't worry what that is yet. It's fine. But yeah, really, what I really wanted to emphasize with this is that even though this is the second algorithm that I go over, it's still the same stuff. You're loading in your data sets, you're splitting your data sets, you're running your fit function. Well, you select what model you want, set some parameters for the model depending on the model itself, run your prediction, run your training with the fit function, and then just run your prediction. Here the prediction is happening on the graph itself, because when we're drawing it, we can see the line is in the right spot or not. But also the score function will do the testing for you. So if I wanted to feed it a point to test if it works or not, you know, I could just run it by calling my predict function and then see if it works. Like for example, let's just say log reg dot predict, and then let's feed it in. We're only doing 2 classes, so I don't know. 1 and 1, or 1 and 2. Well, actually, let's do 2 and 1. Okay, so like the length and the width. And we'll probably have to make those NP arrays. And then the target, I'm going to guess. Okay, well, yeah, you don't have to feed it a target. It's going to return to us a target, I think. Okay, let's see if that runs. So if it requires it to be an NP array. Expected to the array. Yeah, so it's probably an NP array. How did I do that before? I forget. Just copy and paste it to make life easy. I just need 2 square brackets. There we go. Okay, so it basically gave us class 0. If that's right or not, I don't know. I mean, it's just what it's predicting based on the size. So if we give it something of 2 to 1, it's basically telling us it belongs to class 0. So which one's class 0? Actually, I don't think about that. We didn't put like labels in this, but probably the blue one. But either way, you can see that the model works and you can feed it new data to see. Let's feed it some garbage, like massive numbers. I'm curious what it just makes the assumption to be. Class 2. So that's probably like this one up here. In fact, actually, oh, here we go. You can actually see in matplotlib, if you see the bottom right here, those are the numbers of x and y's. And so the really big number would be like way up here. Where would the one that I said earlier, the 2, 1 be at? Probably at, well, the graph ends about 3 here. And 1's about also off grid. So it's actually like way off the chart here. Probably like down here. So it's hard to see. But like, let's pick a number that is clearly in the blue, which is like 4, 4. Class 0. So definitely class 0 is the blue one then. So yeah, so even though the line extends, that 2, 1 is probably right above the blue line, or the blue area. Okay? Oh, actually, look. It's really tiny, but there's the class number too. See that? 0, 1, 2. That's my dog. But yeah, so there you go. Okay? So just like before, you can call predict function and feed it new data. After all, if you're doing this to train a model, it's because you want to use it to predict new stuff, right? So it's useful to actually know that. So yeah, but there's no, you should start to get the idea that like running these machine learning models, it's very easy. The hard part is knowing what to run and how, like what settings to run it so that it is fast, but also high accuracy or low error, better term. And in general, just that it can run in your computer, not just fast. Because I mean, like, whether it's fast or not, but if it requires like 1,000,000 terabytes of RAM, then you're not going to get anywhere, right? So that's kind of what I'm getting to. It has to be fast. It has to be viable to train and to run. Actually, training it is the hard part. Even running something through a neural network, it's really fast. Like when you just want to predict one single value. It's just feeding it to a math formula, essentially. You just compute it and get it out. The training part is the slow part. So like that's the other beautiful thing. Like once you train an algorithm, even if it takes weeks to train this model that like works really well at like self-driving or whatever, once it's ready to go, feeding it new data to test what it belongs to, it's super fast. So That's also the big powerful thing. If it took a long time for this to predict something, then it would be useless, right? You want it to be able to predict things fast, and they can. These models can predict things quickly as long as they're actually trained good. And they work, like the training worked. It's important to put that out there too. Okay, so I think that's long enough as it is now. Like I said, we'll keep going on this in the next video. But for now, hopefully you get a good example. Try it out on your own. And thanks for watching. See you on the next one.